Okay, let's unpack this. Today we're taking a deep dive into a truly fascinating collection of physics questions and answers. Imagine everything from, the science of stopping your car to the incredible life cycle of stars and even how your headphones make sound. We've got it all.
Yeah, and what's truly fascinating here is how these, well, seemingly disparate topics are all governed by just a few fundamental principles. We're going to try and connect those dots for you, reveal the underlying rules that shape our physical world, and I think you'll walk away with some genuine aha moments, Jeff.
Absolutely. Our mission today is to distill the most important nuggets of knowledge from mechanics, waves,
Yeah.
electromagnetism, maybe even a bit of astronomy. Give you a shortcut to being well informed without getting, totally overwhelmed by the details. Let's jump right in.
So ever wonder what really affects how quickly your car stops? I mean, it's clearly far more than just how hard you hit the brake pedal.
Exactly. And this really raises an important question for all of us, doesn't it? How much control do we truly have over these critical factors in our daily lives? That's a great point. Beyond just speed, factors like poor road conditions, think wet, or maybe icy surfaces, they dramatically increase braking distance. And it's not just the road. Things like warm brakes or tires also significantly reduce the friction you need to slow down.
Right. Less friction, longer stopping time.
Precisely. And when we talk about how quickly a car decelerates, we're essentially talking about how a resultant force on a mass produces acceleration, or, well, deceleration in this case.
Yeah.
That classic F equals m times a.
The cornerstone of mechanics, really.
So if a car experiences a braking force of, say, 7,200 newtons, and it weighs 1,600 kilograms,
Uh-huh.
that works out to a pretty significant deceleration of 4.5 meters per second squared.
Which is quite a jolt.
Yeah. And for a real world perspective, if you're doing 80 kilometers per hour, your stopping distance is around 73 meters.
Think about that for a second. 73 meters. That's roughly the length of two large semi-trucks, end to end. This isn't just some abstract number. It's a critical safety insight. It really highlights how dramatically that distance increases at higher speeds, making seemingly small differences in road conditions or tire wear incredibly dangerous.
It really underscores the importance of vehicle maintenance and just, attentive driving.
Absolutely.
So shifting gears slightly, small area, big pressure,
Yeah.
something we see every day, right?
Yeah.
Like think about the difference between walking across maybe soft ground in high heels versus wearing snowshoes.
Oh, yeah. Perfect everyday example. One sinks right in, the other floats on top.
Exactly. It's all about how that same force, your body weight, gets distributed. On high heels, it's concentrated into these tiny points, creating immense pressure.
Whereas snowshoes spread that force out over a much larger area.
Reducing the pressure, letting you stay on top. That's the principle of pressure. Force distributed over an area. The equation being P equals F over A.
Simple but powerful.
So if you're applying a force of, say, 60 newtons, and it causes a pressure of 120,000 pascals,
Uh-huh.
the area that force is applied to is actually incredibly small, just 0.00005 square meters, or 5 times 10 to the minus 4, if you prefer.
Tiny. It really shows how effective concentrating a force can be.
Okay, now, let's pivot from cars and pressure to something a bit bouncier, springs.
Mm-hmm.
When we say an object is elastically deformed, what do we actually mean?
It simply means it's been stretched or maybe squished, but it snaps right back to its original shape once you remove the force. Think of a rubber band or, trampoline, springs in a mattress.
Okay, so it remembers its shape.
Exactly. It's a fundamental property that dictates how things deform and rebound. But what's the underlying rule? How can we predict how much a spring will stretch?
Great question. That's where Hooke's law comes in. It beautifully describes the relationship between the force you apply, F,
Yep.
how much it extends, E, and its inherent stiffness,
Yeah.
which we call the spring constant, often written as K.
Ah, yes. Hooke's law. F equals K times E.
That's the one. And you can actually figure out that K value experimentally. If you hang weights on a spring, measure the extension.
Right, like in a school lab setup. Clamp stand, ruler.
Yeah, exactly. Just need to be careful. Maybe put some cushioning underneath in case the weights fall. Risk assessment is always key.
Good point. Safety first.
So you plot force against extension on a graph. If you get a straight line that goes through the origin,
Uh-huh.
that tells you the extension is directly proportional to the force you applied. The gradient of that line is the spring constant K.
So if the gradient was, say, 2.0 newtons divided by 0.025 meters of extension.
Then K would be 80 newtons per meter. Simple as that.
And that's stored energy in the stretched spring.
Elastic potential energy, EPE. The equation for that is E equals a half KE squared. So for instance, if you had a spring with a constant K of 13 newtons per meter and you stretched it by 20 centimeters, which is 0.26 meters, careful with units,
Always watch the units.
then the stored EPE would be 0.26 joules.
And that's the real insight here, I think. This seemingly simple K, the spring constant, it dictates the behavior of so many different systems, from the gentle bounce in your mattress, like you said, to the really precise mechanics of a watch, or even shock absorbers in cars.
Right.
It's like the hidden personality of a material, showing how much it resists change and how it stores energy when deformed.
Okay, let's zoom out now from the, well, maybe mundane to the truly cosmic. Let's talk about stars. It's incredible to think about why a main sequence star, like our own sun, is so remarkably stable for billions and billions of years.
It really is a marvel of cosmic engineering, isn't it? It's all about balance.
Absolutely. You've got this immense force of gravity constantly trying to pull everything inward, trying to make the star collapse under its own weight.
Crushing pressure.
But it's perfectly counteracted by the outward radiation pressure. This pressure comes from the ferocious fusion reactions happening deep within its core. Hydrogen smashing together to make helium.
Releasing enormous amounts of energy.
Exactly. It's a cosmic tug of war with gravity pulling in and radiation pressure pushing out, holding it in this perfect equilibrium for most of its life.
Amazing stability.
And then what happens? What's the next stage for a star like our sun after it leaves the main sequence?
Well, it enters a fascinating, almost dramatic end-of-life sequence. First, it expands massively into a red giant.
Swallowing nearby planets, potentially.
Potentially, yes. Then it sheds its outer layers, leaving behind a super dense core called a white dwarf.
And eventually,
Over unimaginable timescales, trillions of years, that white dwarf cools down completely, theoretically becoming a black dwarf, though the universe isn't old enough for any to exist yet.
wow. Okay, now shifting focus slightly. When we look at distant galaxies, we observe something called redshift. How does that tell us about their movement?
Redshift is essentially the light from distant objects getting stretched out towards the red end of the spectrum as they move away from us.
Like the Doppler effect for light.
Precisely. So, if we see Galaxy A showing the smallest change in its visible light wavelength, the smallest redshift, that tells us it's the closest one to us, relatively speaking, and moving away from us at a slower speed compared to galaxies with a larger redshift.
Which would be further away and receding faster.
Exactly. And if we connect this to the bigger picture, the redshift of galaxies isn't just about individual movement, it's direct, compelling evidence that the entire universe is expanding.
Space itself is stretching.
Yeah, it's one of the absolute cornerstones of modern cosmology. Truly a mind-boggling thought.
Bringing it back down to Earth, or at least closer to home. Let's talk lenses. How do they work to manipulate light and, well, shape what we see?
Well, it's fascinating because different types of lenses transform light in such different ways. For instance, what kind of image do you typically get from a concave lens compared to a convex one?
Okay, good distinction. If you look through a concave lens, maybe like the people on a door, the image you see will always be virtual and diminished, meaning it appears smaller than the object, and it seems to be located behind the lens itself, where the light rays appear to diverge from. You can't project it onto a screen.
Right, virtual. And convex?
Convex lenses, the magnifying glass type, are the opposite. They converge light rays. They can form a real inverted image on the opposite side of the lens, an image you can project.
Like in a camera or a projector.
Exactly. And here's a neat trick. As an object moves further away from a convex lens, its image actually gets closer to the lens.
Interesting relationship there.
And speaking of measurements, especially in science labs, understanding uncertainty is just crucial, isn't it? It tells you how reliable your data is.
Absolutely vital. You need to know the limits of your precision.
So if you're taking a series of readings, let's say 1.9 centimeters, 1.7 centimeters, 2.2 centimeters, and 1.4 centimeters.
Okay. Quite a bit of variation there.
Yeah. The spread, or the range, is the difference between the highest and lowest. 2.2 minus 1.4, which is 0.8 centimeters. And the uncertainty is typically taken as half that range. So in this case, you'd quote your measurement with an uncertainty of plus or minus 0.4 centimeters. It's about being honest about that wiggle room in your data.
That's a fundamental part of good experimental practice. And sticking with light and perception, here's a fun puzzle for you.
Yeah.
Why would a blue object appear black if you shine only a red spotlight on it?
Oh, that's a classic. It catches people out sometimes.
It does.
It's because the blue object primarily reflects only blue light.
Yep.
That's why it looks blue in white light, which contains all colors.
Uh-huh.
But when a red spotlight hits it, there's no blue light in the red light for the object to reflect. so it absorbs the red light instead.
And since no light gets reflected back to your eye,
The object simply appears black. It's reflecting nothing.
it really makes you think, doesn't it?
Mm-hmm.
How much of what we see is actually about what's not being reflected back, and how much is fundamentally about the light source itself?
Definitely. Our perception of color is truly a dance between the object's properties and the light hitting it. Okay, speaking of light, let's cast a wider net now over the whole electromagnetic spectrum. It's not just visible light, obviously.
No, it's this huge range: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays.
Right. And they all have uses. Ultraviolet light, for instance, UV. It has some very practical uses, doesn't it?
Oh, absolutely. Its high energy makes it great for sterilization, sterilizing water supplies or medical equipment because it can effectively kill germs and bacteria.
Useful stuff. And despite their different energies and uses, they all share some fundamental properties. What's a key one?
The big one is their speed in a vacuum. They all travel at the same incredible speed, the speed of light, see?
Which is roughly 3 times 10 to the power of 8 meters per second. Incredibly fast.
Mind-bogglingly fast.
So if you know the speed, c, and you know the wavelength, lambda, you can calculate the frequency, f, using the wave equation. Speed equals frequency times wavelength.
See,
Yep. So say you have UV light with a wavelength of 300 nanometers. First, convert that to meters. Nano means 10 to the minus 9. So it's 300 times 10 to the minus 9, or 3 times 10 to the minus 7 meters.
okay, got the wavelength in standard units.
Then frequency is just speed divided by wavelength. So 3 times 10 to the 8 divided by 3 times 10 to the minus 7.
The threes cancel. 10 to the 8 over 10 to the minus 7 is 10 to the power of 15.
Exactly. 1 times 10 to the 15 hertz. A very high frequency.
Which makes sense for high-energy UV light.
And just to place things, if you were looking at a table of EM waves, maybe labeled E, F, G, E might be X-rays, F could be visible light, G might be infrared, each with different wavelengths and frequencies.
Right, different parts of that vast spectrum.
Now, thinking about waves more generally, not just EM waves, there's a key difference between transverse and longitudinal waves. Can you remind us?
Sure, it's all about the direction of the oscillation compared to the direction the wave is traveling. In transverse waves, like light or ripples on water, the oscillations are perpendicular at right angles to the direction of energy transfer. Think of shaking a rope up and down. The wave travels along the rope.
Okay, up and down movement, wave travels sideways.
Right, but in longitudinal waves, like sound waves or waves in a slinky, you push and pull,
Uh-huh.
the oscillations are parallel to the direction of energy transfer. Compressions and rarefactions moving along.
Got it. Push-pull movement, wave travels in the same direction. That distinction is pretty vital, right?
Absolutely. It determines how waves interact with matter, how they propagate through different mediums.
And back to experiments for a second. Why is it always drilled into us to take multiple measurements and then average them? Why not just measure once carefully?
Well, it's all about dealing with errors, specifically random errors. Every measurement has some degree of random fluctuation, slight timing differences, reading scales slightly differently.
Right. Unavoidable little variations.
Exactly. By taking multiple readings, say you measure the time for 10 waves to pass 3 times and you get 8.4 seconds, 7.8 seconds, 8.1 seconds.
Okay.
You calculate the mean, the average. Here, that's 8.4 plus 7.8 plus 8.1 divided by 3, which is 8.1 seconds.
So averaging smooths out those random highs and lows.
Precisely. It reduces the impact of any single random error and gives you a much more reliable and accurate estimate of the true value. So the frequency here for 10 waves in 8.1 seconds would be 10 divided by 8.1.
Which is about 1.2 hertz.
Roughly, yeah, about 1.2 hertz. It improves your confidence in the result.
Okay, that makes sense. And here's a neat experimental trick.
Yeah.
If you want to measure wave speed, but it's hard to measure the wavelength directly, how could you do it?
Well, speed, frequency, x wavelength. We just saw how to get frequency reliably by timing multiple waves.
Right.
So the challenge is the wavelength. You could try to freeze the wave motion using something like a strobe light and then measure the distance between crests, maybe using video analysis to help.
So capture an image of the wave pattern.
Yeah, essentially. Then you have both frequency and wavelength, and you just multiply them together to get the speed.
Clever.
And, what's truly fascinating here, bringing it back to the EM spectrum, despite all their diverse properties and countless applications from radio to gamma rays,
Yeah.
they're all part of the same electromagnetic family. They all travel at that same incredible speed in a vacuum. It's a really beautiful example of the underlying unity and elegance in physics.
It really is. Okay, let's circle back to forces, but maybe with a bit more complexity now. Thinking about, say, your morning commute if you cycle. The force that actually propels your bicycle forward, that push coming ultimately from your legs. What do we call that?
We usually call that the driving force, or sometimes just thrust. It's the force overcoming resistance, like air resistance and friction.
Got it. Driving force.
And thinking about that force on the pedals, it's not just about making the bike go forward in a straight line, is it? What about the turning effect?
Ah, exactly. Another interesting force application on a bicycle is how that force you put on the pedal, transferred through the chain, creates a moment about the rear axle.
The turning effect.
Precisely. A moment is just a force causing a turning effect around a pivot. The force in the chain acts at a distance from the axle, the pivot, making it rotate.
And this concept of moments is crucial in all sorts of mechanical designs, isn't it?
Absolutely. From designing gears and levers to just opening a door easily.
Leveraging rotational forces.
Now, if you're looking at a velocity time graph for something like that bike,
Yeah.
how do you find the distance traveled between 2 points in time, say from time y to time z?
The distance traveled is always represented by the area under the velocity time graph between those 2 points.
Right.
So if the graph section between y and z forms, say, a trapezium shape,
Uh-huh.
you just calculate the area of that trapezium. The formula is half times sum of parallel sides times the distance between them. On the graph, that's half initial velocity plus final velocity times the time interval.
So if the velocity changes from 6 meters to 4 meters over 4 seconds,
Okay, so that's half times 6 plus 4 times 4. Half of 10 is 5 times 4 is 20.
so 20 meters traveled in that time.
Yep, 20 meters.
And if a bicycle changes speed, say by 2.4 meters per second over a distance of 0.018 kilometers, first convert that to meters.
18 meters.
Right, 18 meters.
How would you calculate its acceleration, assuming it's constant?
For that, you'd likely use one of the kinematic equations, the ones that link initial velocity, u, final velocity, v, acceleration, a, and distance, s. The most useful one here is probably v a volley u plus 2a's. You know the change in speed, so you know you v, s 18 meters, so you can rearrange to find a.
Let's say the final speed squared minus the initial speed squared divided by twice the distance gives you the acceleration. In this specific case, it works out to 0.16 meters per second squared.
Okay, a fairly gentle acceleration.
And finally, remember that forces aren't always acting in the same direction. They can be vectors.
Right, magnitude and direction. So if you have, say, a force of 200 newtons acting horizontally and another force of 75 newtons acting vertically on the same object,
How do they combine?
they combine to form a single resultant force. You can find its magnitude using Pythagoras' theorem, square root of 200 bottle plus 75 butter.
Which comes out to about 213 newtons.
About 213 N, yeah. And you can find the direction, the angle above of the horizontal, using trigonometry, specifically the arctangent of opposite adjacent, so arctan 75200.
Which is around 20 degrees, maybe a bit more.
Roughly 20 degrees above the horizontal. It's all about adding vectors, head to tail, or using components.
And connecting this back, understanding moments and vector addition is just crucial for efficient design.
Yeah.
From how a bicycle is built to be stable and efficient, to how easily a door opens with the handle far from the hinges, or how a wrench multiplies your effort on a nut. It's all about leveraging rotational forces and combining forces correctly.
Absolutely. Okay, for our final section, let's do a deep dive into how electricity and magnetism dance together. This influences everything from the sound in your ears to huge industrial applications. The key effect used in something like a loudspeaker, for instance. What's that called?
That relies on something called the motor effect.
The motor effect. Okay.
It's incredible, really, to think that the very device producing sound in your headphones or speakers relies on this elegant interplay between electricity and magnetism. How does that motor effect actually, orchestrate sound from an electrical signal?
It's surprisingly elegant, actually. You have an alternating electrical current one that changes direction rapidly flowing through a coil of wire.
Okay, AC current in a coil.
And this coil is placed within a magnetic field, usually from a permanent magnet.
Right.
Now, the motor effect states that a current-carrying wire in a magnetic field experiences a force. Because the current is alternating, the direction of the force keeps switching back and forth.
Ah, so the coil is pushed and pulled rapidly.
Exactly. This force makes the coil and the speaker cone attached to it vibrate back and forth very quickly,
And those vibrations push the air.
creating pressure waves in the air, which are the sound waves that travel to our ears. It's a direct conversion. Electrical energy to mechanical vibration to sound energy.
Neat.
Now, thinking about experiments involving electromagnetism, sometimes results just can't give you a valid conclusion. When might that happen?
A common pitfall is changing too many things at once. If you're investigating, say, the force on a wire in a magnetic field, and you change both the number of turns in a coil and the frequency of the current simultaneously.
Ah, okay. Two variables changed.
Yeah. Then if you see a change in the force, you have no way of knowing if it was due to the change in turns, the change in frequency, or some combination of both. You haven't isolated the variables.
So you can't draw a clear, valid conclusion about the effect of either one individually.
Exactly. It's a crucial point for designing any good experiment, really, in any field. Control your variables.
Right. So if you are trying to predict the motion, the force, on a current-carrying wire or rod in a magnetic field, what's your go-to rule for figuring out the direction?
My go-to is definitely Fleming's left-hand rule. It's such a handy mnemonic.
Okay, talk us through it.
So you use your left hand, point your first finger in the direction of the magnetic field, north to south. Point your second finger in the direction of the current, conventional current, positive to negative.
Okay, field, current.
And then your thumb will point in the direction of the resulting force or motion on the wire. FBI, math or force, field, current.
Thumb, force motion, first finger, field, second finger, current.
Got it. And it predicts motion perpendicular to both the field and the current
I
level.
was perpendicular to both, yes.
Yeah.
Very useful for predicting motor behavior.
And if you wanted to increase that force on the rod or wire, what are the simplest things you could change?
Well, the force depends directly on a few factors. The formula is FBIL, where B is magnetic field strength, I is current, and L is the length of the wire in the field.
FBIL. So the two simplest ways to increase the force, F, are 1, increase the magnetic field strength, B, maybe by using a stronger magnet,
Makes sense. Stronger magnet, bigger push.
and 2, increase the current flowing through the wire. More current, more moving charge, bigger force.
Okay, stronger field or more current. Got it.
You could also increase the length L of the wire within the field, but often the first two are easier to adjust.
Right. Let's see the FBIL in action with some numbers, maybe follow it through. Suppose you have a rod with a tiny mass, say 0.0004 kilograms.
Okay, 4 grams.
Carrying a current of 1.7 amperes, sitting in a magnetic field of 0.3 Tesla, and the length of the rod in the field is 0.05 meters.
Okay, so B 0.3 T, I 1.7 A, L 0.05 meters.
So the force, F equals 0.05, would be 0.3 times 1.7 times 0.5 newtons.
Let's see, 0.3 times 1.7 is 0.51 times 0.05. That's like dividing by 20.
0.0255 newtons.
Exactly, 0.0255 newtons. Not a huge force, but measurable.
Okay.
Now, if that's the only horizontal force acting on the rod, mass 0.0004 kilograms, what acceleration would it cause?
Back to FMA. Acceleration equal Fn. So a 0.0255 newtons, 0.004 kilograms.
Which is, let's see, 25.5, 6.375 meters per second squared.
Spot on. 6.375 meters squared.
Yeah.
Quite a significant acceleration for that little rod.
Because its mass is so small.
Right. And one more step. If that force and therefore that acceleration acts for, say, 0.15 seconds, starting from rest, what final velocity would the rod reach?
Okay, using another kinematic equation, VU plus at, since it starts from rest, initial velocity U,
So V at,
V equals 6.375 meters per second, so that is 0.15 seconds.
which comes out to be 0.956, let's say you're 0.96 meters per second.
So in just 0.15 seconds, it gets moving quite respectably fast.
Yeah, it's a nice chain reaction to physics principles. FBIL gives the force, FA gives the acceleration, and V at gives the final velocity.
It's truly fascinating, isn't it, how that relatively simple principle, the motor effect, FBIL, can be scaled up to power entire industries, think massive electric motors and generators, or miniaturized for our personal devices like those loudspeakers we talked about, or tiny motors in phones. It's such a core concept driving so much of our modern world. It really shows the incredible versatility of fundamental physics.
So what does this all mean? Where have we been today?
Mhm.
We've journeyed from, well, the very practical physics of stopping your car, all the way out to the incredible life cycle of a star. We've explored the subtleties of light and lenses, sound waves, the whole electromagnetic spectrum,
Yeah.
and even delved into that powerful dance of electricity and magnetism.
Yeah.
It's truly amazing how interconnected all these concepts are, isn't it? Revealing the sort of hidden rules of our universe.
Indeed it is. And every calculation, every observation we've discussed, it just reinforces the idea that the universe operates on these predictable, understandable principles. Understanding these fundamentals isn't just about, getting the right answer on a test. It's about developing a framework for understanding the world around you. Encouraging that essential critical thinking that helps you navigate complexity, whether it's technology or just everyday phenomena.
Couldn't agree more. And that's our deep dive for today. So here's a final thought for you, the listener. Consider just how many everyday devices you use that rely directly on the principles we've discussed today. From your phone's screen, using principles of light, and maybe even the speaker using the motor effect, to the very way your car moves and stops using forces and energy. Which one makes you stop and think, here's where it gets really interesting?
Mm,
Something to ponder.